All right, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's our modest crowd today? How's everyone doing today? Tired, probably. It's right before spring break, so I know it's probably one of the hardest lectures to get up for. Yeah, probably one of the hardest lectures to get up for. The one right before the break, and so you guys are here. I just want to say I appreciate it, and for everyone that's gonna be watching on the YouTube recording, good job. My day's been good. I've had a lot of meetings today. So it's kind of like the pre-break rush of meetings, and so everyone wants to kind of meet right before the spring break, and so a lot of those. But besides that, doing good. Okay, and so the plan for today is we're going to be finishing up our lecture notes on internal convection, and so we don't have a homework assignment on this yet, but you can expect one after the break. And then I don't think that's going to take us the whole time. And so I think probably we'll finish up maybe 20, 30, 40 minutes. After that, we'll start the next set of lecture notes on free convection. Okay. All right. So besides that, we have homework 4 that's due Friday. And so homework 4 is based on external convection. And so before I get started today, does anyone have any questions on homework 4 or just anything else I can answer before we get started? Okay. All right. So if there's no questions, let's go ahead and get started. Okay. And so I think today's probably the last day that we'll be covering internal convection, right? So it's kind of like our second major topic inside this kind of mega unit on convection heat transfer, right? And so before this we went over external convection, and then kind of you can almost think of it like the opposite of that is internal convection, right? And remember, the whole idea is that we have a flowing fluid inside a confined space. Okay, so we have a, most commonly, you'll see this occur in some kind of cylindrical pipe. Okay, and so we have some fluid flowing here. And so we have a fluid flowing in a confined space. Okay. Most commonly a pipe. Okay. And so, this is different than our external convection, because external convection, we had everything was kind of free from there, right? And so this is a bit different because, now, our space is confined, and whatever heat goes in and out, the fluid can really feel that. Okay. Okay. And so what I mean by feel is that, whenever you have heat that's exchanged between the fluid and the surrounding walls, what's going to happen is that the mean temperature of the fluid is going to change. Right. And so, that kind of adds an additional wrinkle to these problems that hasn't been seen before. Okay. But usually, what we're interested in, because this is something in the convection unit, we're usually interested in solving for what that convection coefficient is. Right? And so that's kind of the theme of this whole unit on convection. Right? And so we're on the quest to solve for H in all different manners of flow conditions and geometries. Okay. And so for internal flows, we actually have 2 different ways that we usually solve for H. Right. All right. And so one way that we can solve for H is we can use the equation for the mean temperature. Right. And so those were our equations for Tm of x. Right. So we did an example of that last time. Okay. And then the other path that we can take is kind of the more common path for convection problems, where we use the Reynolds number. Okay. And what we saw last time was that for internal flow, we had very simple expressions for the Reynolds number. And so the Reynolds number will either be 4.36 or it'll be 3.66, okay? And that depends on whether we have a constant heat flux at the wall or a constant surface temperature at the wall, okay? Okay. And the same thing actually for Tm of x. And so for Tm of x, our mean temperature equation, you know, we had different expressions depending on whether we had a mean heat flux or a constant heat flux or a constant surface temperature. Okay. All right. And I think the very last thing that we saw, you know, right before we signed off on Monday, was that this path right here, where we use these Reynolds number correlations, this is only valid when we have laminar flow. Okay. And so if you have turbulent flow, then you can't use a Reynolds number correlation. Actually, there's one that you can use later that we'll see. But for now, you know, these simple Reynolds numbers, you know, 4.36 and 3.66. This is only for laminar flow. Okay. All right. And so this was just kind of a recap of, you know, how we got to this point. And so the first thing I want to do today is I want to give you an example of how to actually use this stuff. Okay. And it's going to be an application that might be surprising to you. And so it's, you know, it's actually going to be a biological example involving blood flow, actually. Okay. All right. So any questions on any of this? Okay. So let's go ahead and do an example of blood flow. Okay. And so normally, you know, you don't think about blood when you think about, you know, heat transfer or, you know, or engineering kind of in general. And, you know, but, you know, your blood vessels and the blood flowing through your body, you know, obviously they serve a lot of purposes like transporting oxygen in your body. They also help you fight diseases. But a lesser known function of the cardiovascular system is it kind of acts as the body's own heat exchanger. Okay. And so, you know, the primary way that heat moves through your body is actually through the bloodstream, right? And that's really important because, you know, there will be times when, like, say, you know, you're working out or something and your muscles are heating up because you've exerting them a lot. You know, the heat from your muscles has to leave your body in some way, right? And so your blood actually does a lot of work in actually taking the heat from one part of your body and then transporting it to another, right? And so actually, you know, if you ever notice, you know, when you're in bed too, you know, you feel a lot more warm when you cover up your feet. And so your feet actually are a unique part of your body where the blood vessels are relatively close to the skin surface. And there's actually very little hair there as well. And so because of that, you know, you have kind of maximum convection heat transfer on your feet to your blood vessels. And so if you cover up your feet, you know, that ends up making you warm. Or if you're like me, you know, I actually like to keep my body relatively cool when I sleep. So I actually put the blanket over most of myself, but then I poke my feet out from under the blanket. That's usually the most comfortable to me because then that keeps me from getting too stuffy, but I'm still, you know, warm and I don't get sick when I sleep. Okay. All right. And so if we draw a diagram for that, it might look something like this. And so it looks like just any other internal flow, you know, situation. And so through here, we have we'll say we have a mean velocity. So we'll call that UM, okay? And then on the outsides here, we have, we'll say we have some tissue of some kind. Okay? So this could be like muscle tissue. It could be like, you know, fat tissue. It could be, you know, a lot of, you know, any kind of tissue in your body. Okay? Okay. And we'll say that the tissue is at a temperature TT, where this TT is a constant. And so, if we go back to, our convection situations, this is a situation where the walls are at a constant temperature. Okay, so it's not the heat flux condition. All right, and in particular for this problem, what we're interested in is the amount that the mean temperature is going to change from one part of your body to another one. Okay, and so on this left-hand side, let's say that the mean temperature of the blood, we'll call it TMI. And then on the other side, we'll say that the mean temperature is going to change to TMO, okay? And so the I and the O stand for inlet and outlet, basically, okay? And then the diameter, we'll say the diameter of the blood vessel is given by D, okay? All right. And so in this problem, what we want to solve for is actually the length of these vessels, okay? We want to find the length of vessel needed in order for the blood temperature to reach within 5% of the tissue temperature. Okay. And so basically what that means is that TMO here, that's within about 5% of whatever that tissue temperature ends up being, okay? And we're going to assume the tissue is at a constant temperature, right? And so we're going to do this under two situations. And so we're going to do it for a what I call a relatively large artery, okay? Okay. And so these are kind of the bigger blood vessels that you have in your body. And then the other condition that we'll go over is for a capillary, okay? And so a capillary, if you've heard that term before, those are basically the tiniest blood vessels that you have in your body, that they're literally just big enough for one blood cell to squeeze through. And these are kind of the smallest ones. So here we have kind of a range from kind of the biggest blood vessels that we have and the smallest ones, right? All right, so let's characterize the diameter of both of these types of blood vessels. And for a large artery, we have the diameter is about 3 millimeters, okay? And for the capillaries, the diameter is much smaller. And so it's going to be 0.008 millimeters, okay? And we can also characterize the mean velocity. And so for the large arteries, they have a mean velocity of around 130 millimeters per second. Okay, and then for your capillaries, they have a mean velocity of about 0.7 millimeters per second, okay? And so we're going to solve this this problem under basically both of these conditions, okay? All right, any questions on the problem setup? Okay. All right, and so first thing we're going to do is we're going to compute the Reynolds number to determine whether this is laminar or turbulent flow. All right, and so first let's do it for the large arteries. Okay, and so for the large arteries, we're going to compute Reynolds number is going to be equal to rho mu m d divided by mu, okay? And I just realized I forgot to give you the properties, okay? So let me go ahead and give those to you as well. Right, so the properties of blood, we're going to use the following. And so let's say that the density is 993 kilograms per meter cubed. Let's say that the specific heat, CP, so this is going to be 4,178 joules per kilogram K. Okay. The viscosity, and so I'm going to give it to you in terms of dynamic viscosity. And so this is 695 times 10 to the minus 6 newtons second per meter squared. Thermal conductivity, we'll say it's 0.628 watts per meter K. And then the Prandtl number is 4.62. Okay, so that's better. So now you can basically plug in, for everything for the Reynolds number. And then for the large arteries, once we plug all these numbers in, what we get is a Reynolds number of 557. Okay. And then for the capillary, we can do the same thing. And so for the capillary, we're going to do rho um times d divided by mu. Okay. And so this is going to be 0.008. Okay. Right. And since both of these are less than 2300, this means that the flow in both the large artery and the capillary are going to be laminar. Okay. And so that's great. And so since the flow is laminar, we'll be able to use our Nusselt numbers, which will simplify our calculations quite a bit. Okay. And this is I didn't just make up numbers for this to be laminar. So this is actually pretty common in your blood vessels. And so, for blood flow, it's actually one of those unique systems where the flow doesn't often go turbulent. And so it's basically laminar all throughout. And so it's kind of nice because it makes these calculations much simpler. Okay. And so since our flow is laminar, and since we have a case of a constant surface temperature, okay, then we know that our Nusselt number is going to be 3.66. Okay. And then this is going to be equal to H times D divided by KF, right? And so what we can do now is we can set up this equation for both the large artery and the capillary and use that to solve for H, okay? All right, so any questions on this? Okay, all right. And so let's solve for H. Under both conditions.
Professor?
Yep.
Do you think you can go back just for like 2 seconds?
Sure.
Thank you.
Mm-hmm. All right. And so the first, let's do the large artery. And so for the large artery, we have H is equal to 3.66 times KF over D, okay? And so if we plug in the diameter for the large artery as well as the thermal conductivity, what we get is an H value of 703.36 watts per meter squared K. Okay. Right. And so for the capillary, we can do the same thing. And so for capillary, we can do H is equal to 3.66 times KF over D. Okay. Where now we're going to plug in the diameter of the tiny capillary, and what we get is an H of 287310 watts per meter squared K. Okay. All right. And so now that we have H for both of these, and so now we can go ahead and plug this in to our TM equation. Okay. Okay. Because remember, what we want for this problem is we want to solve for the length that's required to, in order to make the temperatures up to 5% of the vessel temperature, right? And so the way that we're going to get that length is we're going to get it from our equation for Tm of x. Okay. All right. And so for a case of constant surface temperature, we have the following equations. We have Tm of x is equal to Tm of 0 minus Ts times exponential of minus pH divided by m dot Cp times x plus Ts. Okay. Right. And so this is our equation for Tm that we had from a previous lecture. Okay. And so what we can do now is we can plug in for the perimeter and the mass flow rate. Right, so the perimeter is just going to be pi times d, right? So pi times the diameter. And then m dot here is going to be rho times um times pi times d squared over 4. Okay. And so we basically just multiply the mean velocity by the density and the cross-sectional area of the flow. Okay. All right. And so ultimately what we're after here, since we're solving for length, ultimately that's going to tell us we need to solve for x, right? So x is basically, remember, x is kind of the axial length down our blood vessel down there, okay? And so let's set up this equation so we can solve for x. Okay, and so let's go ahead and subtract Ts from both sides and then divide by this. And so what we get is Tm of x minus Ts is divided by Tm of 0 minus Ts. Okay, this is equal to exponential of minus pH divided by m dot Cp times x. Okay. Right. And so what we can do here is we can, since we're solving for the length required for the, the temperature to reach 5% of the tissue temperature, what we can do is we can set this whole quantity right here and set this equal to 0.05. Okay. And so what that says is that, initially what we have is a Tm of 0 minus Ts, right? And so that's the initial temperature difference between the wall and the fluid, right? And so once that difference gets to only about 5%, which is, what we have right here up top, that's when, the blood temperature and the surface temperature are within 5% of each other, okay? And so we're going to set that entire left side equal to 0.05 and then continue solving for x. Okay. Okay. So any questions so far on this example? And so if we set that equal to 0.05, this is equal to exponential of minus pH over m dot Cp times x, okay? Right, and so to solve for x, we're going to take the natural logarithm both sides, and that's going to cancel out the exponential, right? And so we have ln of 0.05 is equal to minus pH over m dot Cp times x. Okay. Now we can solve for x. Okay. And so what we get is x is equal to minus ln of 0.05 times m dot Cp divided by pH. Right. Okay. And then what we can do is we can plug in H, you know, and for each of the different examples. Okay. I think m dot is also going to change for the large artery. Okay. And so if we plug in everything from the large artery, what we get is x is equal to 8.7 meters. Okay. And then for the capillaries, x is equal to 3.3 times 10 to the minus 7 meters. Okay. And so you can see, you know, it takes your large arteries a lot longer. Basically, the way you can interpret this is that for the large arteries, it takes a lot more time and a lot more length in order to transfer heat to change the blood temperature, right? But for the capillaries, because there's so little blood that flows into the capillaries, you know, it hardly takes any time at all for the blood temperature to go up. And so, you know, basically the upshot of this is that, you know, whenever you have blood vessels that are close to your skin, because those are going to be the ones that's responsible for exchanging heat between your body and the atmosphere. Usually those are going to be made of very, very small blood vessels, just because they're a lot more efficient at transferring heat than the larger vessels. Okay, your larger vessels you mostly see kind of much closer to the interior of your body, because the job for those is more just to transport the blood places. But for places where you actually need to exchange heat, you know, you're going to have much smaller arteries, and that's going to be a lot more efficient. Okay. All right. So any questions on this example here? Okay. All right. So let's do one more example, just so you can kind of get one more look at the stuff. Right? You can never have enough examples, so we have time for one more. Right? And so let's say that we have water that's flowing in a tube. Okay. So let's say that we have a tube, looks like this. Okay. The diameter of this tube is 50 millimeters. Okay. And the length is going to be 6 meters. Right. And let's say that we know the mean temperature at the inlet and outlet of the tube. Okay. And so at the inlet, this has a mean temperature of 15 degrees C. And then at the outlet, let's say this has a mean temperature of 57 degrees C. Right? And then going into the tube, we have a mass flow rate of 0.25 kilograms per second. All right. And additionally, we're going to assume that the surface temperature is constant, and the surface temperature is going to be 100 degrees C. Okay. And so in this problem, we're going to solve, we're just going to basically just compute the convection coefficient. Okay. And so we have kind of a basic kind of water pipe here with a constant surface temperature. And so, you know, we're going to compute the convection coefficient from this. Okay. And let's assume that the water has a specific heat of 4,178 joules per kilogram K. Okay. And so in this situation right here, you know, we'll actually be able to solve for the convection coefficient using our Tm of x. Okay. Okay. And so it's a little bit different than than our previous problem, because in our previous problem we just used the Reynolds numbers. But for this case, you know, we actually have everything that we need to solve for the convection coefficient using Tm of x. Because remember, you know, Tm of x works regardless if your flow is laminar or turbulent, right? Okay. Whereas the Reynolds numbers that we had, those only work for laminar flow. And so for this case, you know, we can compute the Reynolds number to see if it's laminar or turbulent. And I actually didn't do that for this problem, but because we have everything that we need to plug in for Tm of x, let's go ahead and use that, because that's going to give us a reliable number for the convection coefficient. Okay. And so for this case, you know, we have a case where the surface temperature is constant. And so our Tm of x looks like the same expression that we had from the previous problem. Okay. Right, so first we have the difference in temperature between the at the inlet and the surface. Then we have exponential of minus p times h divided by m dot cp times x, okay, plus ts. Right. All right. And so in this equation here, we actually have everything that we need except for h. Okay. And so that's what we're going to solve for this in this equation right here. Because we actually have x this time. And so since we have the length of the tube, we're just going to go ahead and use that in this expression and use that to solve for h. Okay. All right. Any questions on the setup for this example? Okay. All right. So let's go ahead and start plugging things in. Okay. And so, you know, first thing we have, let's go ahead and simplify and isolate the exponential. Okay. And so on the left-hand side, we have Tm of x minus Ts over Tm of 0 minus Ts. Okay. And so let's go ahead and plug in values for these guys, right? And so we know that Ts right here, Ts is 100 degrees C. Right. Tm of x is going to be the mean temperature at the end of the tube. Okay. And so from this problem, this is going to be Tmo, right? So the mean temperature at the outlet, which we know is 57. Which my iPad is not cooperating right now. 57 degrees C, okay? And then Tm of O right here, or Tm at 0, sorry, this is going to be Tmi, which is the mean temperature at the inlet, which is 15 degrees C, okay? All right, and so just from the properties of the problem, we have everything that we need over there, okay? And so on this side, we have exponential of minus P times H divided by m dot Cp times X, okay? Where again, we have everything on this side. So X right here is going to be the length of our tube, and our length was 6 meters. Okay. M dot we have from the problem, Cp we have from the problem. Perimeter we can easily compute from, from the diameter, okay? And so all we have to do here is we just have to manipulate this a little bit and solve for H, okay? Okay, and so, you can take the natural logarithm both sides, multiply by the by all the other variables, and what you get is an H of 755 watts per meter squared K. Okay. And so this is, the reason I show this example is, this is an example of what you can do if you have everything else in the problem. So you don't have to use a Reynolds number here. You can just use Tm of X to solve for H. And if you can do that, that's usually more reliable because then you don't have to worry about whether the flow is laminar or turbulent. Okay. All right. Any questions on this example here? Okay. And so that's another example of solving for H. But what happens, what happens when we have turbulence? And so we've kind of been sidestepping that issue a little bit in this in these lecture notes. And so it turns out, there is a Reynolds number correlation for internal flow, for internal turbulent flow. Unfortunately, it's not as simple as the laminar case. Okay. And so, if you do want to solve for the convection coefficient with the Reynolds number, and you have turbulent flow, this is basically the expression that you use. Okay. Right, and so you have Reynolds number of diameter, okay, is equal to 0.023 times Reynolds number to the 4/5 times Prandtl number to the n, okay, where n here is a variable that can either be, there's two options for it, and so for it, and so you're going to plug in 0.4 in for n if your surface temperature is hotter than the mean temperature. But if your surface temperature is colder than your mean temperature, you're going to plug in 0.3 in for n. Okay. And so for cases where you can't solve for H from the mean temperature equation, this is basically how you would do it. You just have to be careful on what you plug in for n, depending on whether your fluid is heating up or if your fluid is cooling down. And this is valid actually for both constant heat flux and also constant surface temperature. Okay. All right, any questions on this? Okay. All right, so one more point I want to make for internal convection, and that's talking about the entrance region a little bit. And so if you remember, when we first started talking about internal convection, there is this region at the beginning of the pipe, which I call the entrance region, right? And so, let me go ahead and draw the situation again, okay? And so when fluid first enters the pipe right here, remember what's going to happen is that the boundary layers are going to start to form off of the walls. Right? Okay. And so these right here are boundary layers. Right? And this region where the boundary layers are kind of still developing, and they haven't converged yet, we called this the entrance region. Okay. And so up to this point, we've kind of been ignoring it. And so we haven't done any calculations in the entrance region at all. And that's on purpose. And so the reason for that is the entrance region is very, very complicated. And so it's actually, even for, for experts, it's really hard to like really quantify and characterize what's going on in the entrance region. And so for most analyses, we actually kind of ignore it just for the sake of simplicity, which is not a bad assumption, because a lot of times this entrance region is usually really short, but within that short region, lots of crazy stuff can happen. And so, I just kind of want to let you guys know and kind of, emphasize the fact that usually we kind of ignore what's going on here, okay? But, one thing I do want to mention is that, remember that when we talk about boundary layers, there's two types of boundary layers that can develop, right? And so what I've drawn in blue here is, maybe this is the velocity boundary layer, but there might also be a thermal boundary layer as well, okay? The thermal boundary layer develops, remember, independently of the velocity boundary layer. Okay. And then depending on the Prandtl number, one boundary layer might grow faster than the other one. Okay. And so, in order to actually perform analysis on internal convection, we have to assume that we're outside of the entrance region for both the velocity and the thermal boundary layers. Okay. Right, so both. Oops. Okay. And so, this, usually this is not an issue because most times they converge pretty quickly. But if you have a fluid with, maybe a really high Prandtl number or maybe a really low Prandtl number, so, the Prandtl number is not really close to 1, then you might have a case where one boundary layer will take a lot longer to develop than the other one. And you kind of just have to be aware of that when you're doing your calculations. That, if you have a very extended, thermal entrance region, make sure you take that into account. So we're not going to do anything for that in this class, because in this class we're just going to assume everything is fully developed. But if you are going to be doing, this kind of convection thermal analyses in practice, I want you to kind of be aware that of this phenomenon. Okay. All right. Any final questions on internal convection before we move on to free convection? Okay. All right, and so that's internal convection, and so this is not the last that we'll see of this, and so we'll actually see this again after the spring break when we talk about heat exchangers. And so heat exchangers build off a lot of this internal convection stuff, and so don't forget this. I mean, obviously, this stuff is going to be on the midterm as well, so don't forget for that. But it's going to come up again once we talk about heat exchangers after the spring break. Okay. But for now, let's talk about kind of the third. The third sibling of convection, which is free convection. Okay. Right. And so free convection is kind of almost like the black sheep of the convection family, in that it's the way it works is actually quite different. And let me kind of explain what that means. Okay. All right, and so kind of up to this point, when we've covered external convection and internal convection, what we've kind of implicitly assumed is that the fluid flow is forced across our surface. Okay. And so what that means is that, there's some kind of external force that's kind of driving our flow, right? And so for, like, let's say internal convection, like we have a pump, maybe we have a pump that's driving our flow, or for external convection, maybe we have, wind currents that are driving our flow, but something is forcing the fluid to move, okay? And this is kind of the most common way to generate flow. And so, usually when you have when you want to flow fluid over something, you have to kind of force it yourself. That's just kind of how fluid mechanics works. Okay, but sometimes fluid can actually flow without some kind of external force that's forcing it. Okay. And so, you can actually have fluid flow in situations, without, either someone or the weather or doing anything. Okay. And what this actually relies on, which is kind of surprising, is it actually relies on buoyancy. So hopefully you guys remember about buoyancy back in your fluids classes. But basically the idea with buoyancy is that, if you have differences in density within a fluid, that will cause the fluid that will cause a buoyant forces, right? So differences in density will create buoyant forces. Okay, so good old Archimedes principle, and so hopefully that rings some bells. Okay, and so if you can get a situation where you have differences in density within a fluid, you can have a situation where the fluid will will flow just by the action of buoyancy, right? And so let's consider a situation like this. Okay, so I'm going to make a sandwich. Okay, and let's say that on the bottom here we have fluid that's less dense. Okay. Okay. And on the top here, let's say that we have fluid that's more dense. Okay. And so, what you should remember from fluid mechanics is that if you have, a fluid that's less dense within a fluid that's more dense, what's going to happen is that less dense fluid is going to rise up. Okay. And then the more dense fluid will fall down. Okay. And so this is the exact same physics that drives like a hot air balloon, right? And so in a hot air balloon, basically you're going to heat up the air inside your massive balloon, and that's going to make the density inside that hot air balloon to be much less than the outside air, right? And so because you have much less dense air within the hot air balloon, that's going to want the less dense air within the balloon is going to want to rise up, and that's going to take you with it. And then you can say goodbye to all your friends and family because you're floating away in your hot air balloon. Okay. Right. And so anytime you can create these, what I call density gradients within a fluid, you're naturally just going to create some flow because that lighter fluid is going to want to go up and the heavier and the more dense fluid is going to want to go down strictly just from gravity. Okay. Okay.
Professor, I have a quick question.
Sure. What's up?
If you're in a hot air balloon, wouldn't that still be considered like a forced convection?
Yeah, so actually, so the hot air balloon is there's the fluid itself is you're, let's see. Yeah, so you're not actually kind of physically pushing the fluid. And so when I talk about like forced convection, I think of like a pump that's like physically pushing it. But for the hot air balloon, you're just kind of heating up the fluid. And so you're not actively like pushing the fluid up in the hot air balloon, but you're just kind of heating it up, and just naturally from the density differences, that's causing it to rise.
That makes sense.
Yeah, good question though. Definitely a good point.
Could you say the atmosphere is pushing the air up then?
Yeah, you can. It's actually gravity. So I guess, you know, and technically with buoyant forces, you know, you have an external force that comes from gravity, but you know, we don't create gravity, and so it's we say that's kind of a more of a free flow from that sense. Yeah. Mm-hmm. All right. And so the question now is, you know, how do we actually create these differences in density? So actually, you know, the hot air balloon kind of gives us a hint for this, right? And so what we know about fluid properties is that generally as you heat up a fluid, its density gets less and less, right? And so that's why we have the fire inside the hot air balloon. And so the way that you can actually create free convection is if you have a difference in temperature within the fluid, right? And so let's say that in our sandwich here, let's say that we have a hot plate on the bottom and then a cold plate on top, okay? And so that hot plate is gonna basically heat up the fluid next to it, and by heating it up, it lowers its density, and that's gonna cause it to rise, whereas the cold plate on top makes that fluid more dense, and that's gonna wanna make it fall, okay? And so because you have this kind of, you know, circulating motion right here, this is actually gonna drive some convection heat transfer. And so this whole topic of free convection is basically convection heat transfer that you get strictly just from density differences within the fluid, okay? And so, you know, I'll tell you right now that, you know, if you compare free convection to forced convection is going to dominate, you know, 99 times out of 100, because, you know, even though you do get some flow from these density differences, usually it's not nearly as much as if, you know, if you have a pump in your system, or if you have you know, some kind of fan, or, you know, you have like a windstorm, right? And so usually forced convection is going to be much stronger, but, you know, free convection does have its applications as well. And so there's a lot of engineering geometries and a lot of engineering situations where the free convection will actually be pretty significant, and you can actually use that in your design too. And so what you'll see is that, you know, for a lot of engineering systems, you know, they use this free convection to maybe cut down on, you know, they don't have to buy such a heavy pump, because the free convection will kind of naturally cool or naturally heat up a surface, such that you don't really have to. And so it's kind of a clever thing to kind of keep in mind, you know, when you're designing kind of, usually it's kind of really big industrial applications for these things. Right? Okay, so any questions on this? Okay. All right, and so, you know, we see that, you know, if you have a temperature gradient within your fluid, naturally you're going to have a density gradient. Okay. But it's not that you it's not enough just to have any temperature gradient, and so it needs to be within a certain pattern, right? And so let me draw kind of a sister situation to the one we had before, right? So let's say that we have a sandwich, and so let's say instead of having the hot plate on the bottom, let's have our hot plate on the top, and then let's have our cold plate on the bottom. And so next to the hot plate, we know, when you heat up a fluid, it becomes less dense. Okay. And for, when you cool a fluid down, then it becomes more dense. Okay. And so you have basically less dense fluid sitting on top of more dense fluid. And so it's kind of the opposite situation that we have from before. Okay. And in this situation, since the lighter fluid is already on top, the lighter fluid, remember, the lighter fluid, or less dense, always wants to rise. But it's kind of already at the top of our situation here. And so here we actually have no flow. Okay. Because everyone is already where they want to be, right? And so the more dense fluid is at the bottom and the less one's at the top. And so here you have basically no flow at all. Okay. Okay. And so let's talk about some applications for free convection. Right. And so, usually you see these in pretty heavy industrial application because you need usually first of all, you usually need a huge temperature difference between, your solid and the fluid. And you usually need this to occur over long lengths. Right? And so one application could be in power generation. Right, so these usually involve pretty heavy machinery, big machinery where free convection can be a thing. Next thing would be in basically very large electronic devices. Right, and so things like maybe like a huge server rack, right? So then you have basically a very hot server and maybe a cool air on the outside that's going to generate some flow. Okay. Thermal manufacturing, right? And so any kind of manufacturing that basically requires huge, very high temperatures. And so maybe, you're annealing something or maybe you're baking something in an oven. So, because you have very large temperature difference there, that's going to create, density gradients. Right. And HVAC, and so heating, ventilation, and air conditioning, that's kind of another place where free convection can occur. Okay. All right. And so, basically, what a lot of these have in common is that, a lot of times these are situations where, the geometry itself might be too challenging to maybe put a pump in there. Or it's or you have just very high temperature differences where just you have either a very, very hot surface that's going to generate a lot of just free convection flow. Okay. And so that's kind of where these free convection, that's usually where they come into effect. Okay. Okay, so any questions on this?
Would electronics fall under that category too, or making electronics?
Yeah, I mean, so if you're talking about, like, it all depends kind of on the size. And so for a lot of electronics where, maybe you have that on your desktop, usually, a fan for that one is usually not the hardest thing to install. And so you're going to get much more convection from any kind of forced airflow on top.
I meant by like making the circuit boards themselves.
Ah, I see. Yeah,
Or-
yeah. There, so you'll see kind of the geometry that we usually work with here. So we're going to work with mostly just a vertical plate, and so for circuit boards, they have a decent amount of length. That might be one application where especially if your parts are really heating up, that you have free convection in there. Yeah.
Okay, thank you.
Yeah. All right, and so let's look at the kind of the geometry that we're going to be working with, because this is kind of the simplest one to do for free convection. And so we're going to focus mostly on a vertical heated flat plate. And then this flat plate is going to be immersed in a fluid at rest. And so we're going to assume that the fluid, there's going to be no forced convection here, right? And so visually it looks like this. Okay? So we have a large plate that looks like this. Right? And so U infinity here is going to be 0. And so basically far away from the plate, we're going to have zero velocity. Okay. And the reason I draw it vertical is because gravity is going down just like that. Okay. All right. And so if we say that, this surface right here, and so we'll say that the surface temperature is greater than the ambient temperature, so Ts is equal to greater than T infinity, what's going to happen is that, it's going to drive some fluid flow, right? And so, the fluid right next to the surface is going to heat up. As it heats up, it gets less dense, and that's going to want to make it go upwards. Okay. Right. And so just like before, just like our external convection, we're going to have a boundary layer that forms. Okay. Where the boundary layer, that's basically our transition zone. Okay. And so inside the boundary layer, we're going to talk about, what's the velocity distribution, and also what is the temperature distribution here. Okay. All right. And so let's talk about the velocity distribution first. Okay. And so the velocity profile inside the boundary layer here is going to be pretty unique. So it's going to look quite different. Right? And so if I kind of draw it in this image here, it's going to look like this. Okay. So this is the velocity distribution. Okay. Right. And so what you can see here is that the peak of the velocity, or basically the fastest flow, occurs somewhere in the middle of the boundary layer. Okay. And so this is different. And so if you kind of remember how our velocity distribution looked like in external flow, we reached a maximum velocity at the end of the boundary layer, right? And the reason for that before was the fact that our free stream velocity was our maximum velocity in the system. Okay. So before, U infinity was max velocity in system. Right. And so that's not the case here, because remember, outside of the boundary layer here, we have fluid that's at rest. And so basically inside the boundary layer, we're going to have fluid that starts at rest near the surface, and it's going to end at rest at the outside of the boundary layer, and it kind of reaches its peak kind of in the middle. And so it's a little bit unique, and so that creates kind of an interesting kind of velocity profile here. Okay. And so this is actually going to change which dimensionless numbers that we use as well, right? And so for internal convection and external convection, remember the way that we determined whether the flow was laminar or turbulent was we use the Reynolds number, right? Okay. And if you remember, what the Reynolds number represents, the Reynolds number is a ratio between inertial forces and viscous forces. Okay. And so that was our Reynolds number. But and this worked for external convection and internal convection because the inertial forces that we get, those were driven by our external forcing. So this was coming from our pump, or this was coming from the environment, or what was forcing our flow. And so for free convection, we don't have an external something that's pushing our flow, right? And so we don't have any inertial forces that we can compare here, right? And so for free convection, we actually don't use the Reynolds number at all here. And so we're going to need a new dimensionless number that makes a different comparison of the forces in our system. Okay. All right. So any questions on this so far? Okay. All right. And so for free convection, we don't really care about inertial forces because it's not going to be there. But what we do have instead of inertial forces are buoyant forces. Okay. Okay. And so instead of taking a ratio between inertial forces and viscous forces, what we want to do instead is take a ratio of buoyant forces and viscous forces. Okay. Okay. And so we need a new dimensionless number for this. And thankfully, it already exists. And it's called GR. It's not GR. So GR here stands for the Grashof number. Okay. And so the Grashof number is basically a ratio between these buoyant forces and viscous forces. Okay. And you can even though I know it's a new variable and a new thing to know, but you can basically think of this as the analogous as the basically the equivalent to the Reynolds number for free convection. Okay. Okay. And so we're going to use it in basically the same way. And so for free convection problems, instead of computing the Reynolds number, you're going to compute the Grashof number instead. Okay. And basically what the Grashof number is going to tell us is it's going to tell us whether the flow is going to be laminar or turbulent. Okay. Right. And so this is kind of a big difference between free convection and internal and external convection, is that instead of the Reynolds number, what we're going to compute is the Grashof number instead. Okay. All right. Any questions on this? Okay. And so how do we actually compute this Grashof number? So, we can see here what it represents. And so we can see that it represents the ratio between buoyant forces and viscous forces. But how do we actually compute a number for that? Okay. And so let me go ahead and give you the expression here. So I do have a derivation of this in the notes, but it's kind of lengthy and kind of not really relevant for what we're doing. And so if you want to see the derivation of the Grashof number, you can see it in the notes. Basically, I go from Navier-Stokes and I do some work to introduce temperature into Navier-Stokes, because Navier-Stokes normally doesn't have any temperature, right? But in order for us to, in order to get buoyant forces, we basically need to have a difference in temperature in our fluid. Right? And so the Grashof number is the following. And so we're going to take gravity times beta, and I'll define beta in a second. Then we're going to multiply it by the difference in temperature between our surface and the free fluid. Okay, so this can be T minus T infinity times L cubed divided by viscosity, kinematic viscosity squared. Okay. And so that's how you determine you know, the Grashof number. Okay, and so let's talk about this beta thing, because that's something that's new in this equation. And so this beta you can think of it as the volumetric. It's called the volumetric thermal expansion coefficient. Okay. Its exact mathematical definition is given by the following. So beta is equal to minus 1 over rho, where rho here is density. Okay. And then we multiply it by the derivative of rho with respect to t. Okay. Right. And so basically what this beta represents, how quickly or how much density can change when the temperature changes. Okay. Okay. Because for most fluids, you know, generally what you see is that, like, let's take water for instance. And so for water, you know, if you want to find the density of water at a certain temperature, there's no formula for it, and there's no you know, there's no way to compute that. And so the way that you do that is you kind of look it up in a table based on what people have measured before. And so this beta parameter, you can almost think of it as like a way to kind of mathematically kind of look at the graph of how density changes and then kind of put a single number to it. Right? And so, you know, for our calculations, you know, we're going to do an approximation of this. And so we're not going to, you know, it's a bit hard to compute in practice. But, you know, based on just the film temperature that we'll see, you can get a decent approximation for this guy. Okay. All right. So any questions on this? Okay. And so one last thing before we end for today, just to kind of, you know, set us up for after the spring break. And so, you know, usually, let me switch to black here. Right. So usually when we solve the Neutral number for the Neutral number, you know, what we found before was that the Neutral number was a function of Reynolds number and Prandtl number, right? And so in all of our correlations, basically, we saw that the Neutral number was some function of Reynolds and Prandtl, right? But for free convection, you know, obviously we don't have Reynolds number anymore. And so what we're going to do is we're instead replace this with the Grashof number, okay? And so after the spring break, what you'll see is that, you know, we'll do free convection problems, and we'll see Neutral number correlations with the Grashof number in there instead of the Reynolds number, okay? All right. Any final questions before we wrap up for spring break? Okay. All right. And so that's all I got planned for today. So thank you guys for coming in. You know, today. I know it's the last day before spring break, and so hope everyone has a great spring break. You know, hope everyone is able to rest a little bit, stay safe. You know, stay healthy out there, and I'll see you after the spring break. Thanks,
Thank
you too.
Professor.
Thanks, guys.
Hey, Professor, I had a
Thank you.
quick question.
Sure. What's up?
By any chance, will you be available during spring break for like office hours, or you're on break too?
Oh yeah, great question. And so I won't have my regular office hours on spring break, but I will be available. And so I'm not really going anywhere. I'm just going to be in my apartment. And so if you want to meet up, you ask questions about anything, class related or not, then just shoot me an email and we can set up a meeting for that.
Okay. All right. Thank you very much.
Yep. Mm-hmm.
Have a good one.
You too.
Professor?
Yep.
Could you actually help me with a homework problem?
Sure. Yeah, definitely.
So for number 4, problem F and G, I was having some trouble.
Problem 4,
Yep.
F and G. Let's see. F and G. Okay. And so this is basically after you've computed the convection coefficient, and you're going to use that to for the pipe, right?
Yeah, so for F, I used the equation Q equals to HA times TS minus T infinity,
Mhm.
and then I got a slightly higher number.
How much higher did you get?
So the answer was 16,750, but I got 19,148.
Okay. Did you set up your thermal circuit for this?
Yes, I did.
Okay. And so you have 3 resistors, right? So one for the external fluid.
I actually have 2.
Okay, yeah. So you need the let's see. Yeah, I think you need the thermal resistance for the pipe as well. And so I give you the thermal conductivity of the pipe.
Okay.
And then
Could you
have
kind of go over that?
Oh yeah. And
Thank
so basically you have a situation that looks like this. So you have flow on the outside. And so this is T infinity, U infinity, and then we have a pipe here. Right? And so the pipe has an inner radius and an outer radius. And what I tell you is that inside the pipe, you have Ti and Hi. And so let's see, K pipe. This is 45 watts per meter K. Let's see, inner radius, outer radius. And so we have Ri. What is this? Ri is 10 centimeters. And Ro is 11 centimeters. And then I give you Hi in the problem. Hi is 325. Okay. And then, yes. Okay. And so in parts A through E, I basically have you solve for HO because that's the one that's not given, right?
Mhm.
And so you solve for that using cylinder and cross flow and the Neutral numbers for that.
Yep.
And so once you have HO, you can set up your thermal circuit with 3 resistors. Right? Or the 2 ends of our circuits can be T infinity and Ti. And so on the outside here, we have 1 over HAO. For the middle resistor, we have Ln of RO divided by Ri divided by 2 pi KL. And then for the inner one, we have 1 over HIAI. And then the Q that you solve for is just going to be the Q that goes through this circuit. And so this AO right here, since it's going to be the outside of the cylinder, this is going to be 2 pi RO times L. And then for the AI, this is 2 pi RI L. And then from here, you just take the temperature difference between the two, you divide it by the total resistance, and then that should give you your the Q loss.
Okay.
Yeah.
Yep. I was missing the Ln.
Oh, okay. Yes. Yeah.
Mhm.
So you definitely need to include that one. Mhm.
Okay. And then how would you set up part G?
Yeah. So part G is basically I'm having you compute how much actual energy is lost, and so because right now your Q loss is given to you in watts, right? and watts is joules per second. And so I basically want you to convert this into a unit of energy. But for a lot of power companies, the way they measure energy is not in joules, but they use a unit called kilowatt hours. And so, it's basically kilowatts times hours. And so you're basically getting a unit of energy, but you have to convert basically Q loss into kilowatts. Okay. And then from there, you multiply by however many seconds are in an hour. Because normally, if you compute, when you're converting power to energy, you have to multiply by some time, right? Because the time is going to cancel out the denominator there.
Yep.
And so for kilowatt hours, you just multiply by how many seconds are in an hour. So I think it's 3,600. Let me double check that though, because this always kind of confuses me.
Same here.
Let's see. Okay, and so the conversion is basically 1,675 watts, where watts is joules per second. And then, oh, that's right. So it's the amount of energy lost in a day. And so you basically need to compute how many hours are, or let's see. Okay, let's do this. So we have 24 hours per day, right? And then into that hours, you have 60 minutes per hour.
Per hour.
Oh, I do this in 2 steps, I see.
Okay.
And then you have 60 seconds per minute. And that gives you something, in joules, right? And then I think I just looked up online and said, convert joules to kilowatt hour. And then the way you do that is you divide it by 3.6 times 10 to the 6. And this is joules per kilowatt hour. Yeah.
Okay.
Yeah.
Makes sense.
There's probably an easier way to do it, but I'm part of the millennial generation that relies on Google to do my unit conversions for me.
Yeah, a lot easier.
Yeah.
Okay, thank you.
Yep.
Makes a lot of sense. Okay, have a nice day.
Thanks, you too.
Thank you.